Section: Introduction. In this section, we discuss the significant progress made by large language models in enhancing the capabilities of AI agents in the software industry. We have seen rapid advancements in AI assistant tools like Multion and Adept AI, as well as consumer products like Rabbit R1 and Humane AI Pin, which are becoming popular among users. Research in AI agents has led to improvements in thinking processes and prompting techniques. The emergence of multi-agent systems is a new trend, showing how language models are used to create reliable software that benefits users. These innovations utilize the API calling and reasoning abilities of large cloud-based language models to convert human language instructions into actionable commands. However, there are concerns about using cloud models, such as privacy issues, inference costs, and the need for constant Wi-Fi connection. The cost of interacting with AI bots powered by models like Google's Gemini family and OpenAI's GPT series can be high. For instance, using the GPT-4 API for an hour may cost around 24 United States cents. When it comes to function calling, methods like RAG-based or context-augmented approaches can be costly, requiring processing of about 1,000 tokens per call. To address these challenges, there is a shift towards developing smaller models for deployment on edge devices like smartphones and cars. However, these edge computing-based models face issues like slower latency and limited battery life. Energy consumption for large models can be significant, affecting the number of function calls that can be made on devices. To overcome these obstacles, we have developed a method to improve accuracy and latency for function calling on 2B parameter models on devices, achieving state-of-the-art results. This method involves tokenizing core function names and fine-tuning the model with functional tokens to enhance its understanding of software capabilities. By using functional tokens during inference, the model performs better in function calling compared to GPT-4. Our approach with a 2B parameter model fine-tuned from Gemma 2B significantly reduces context length during inference, enabling more function calls on devices with the same battery and reducing latency per function call. In related works, efforts are being made to deploy smaller-scale language models on edge devices like PCs and smartphones to improve inference speed. Various open-source models of manageable sizes have been introduced, and research initiatives like Llama CPP aim to enhance inference speed on devices. Projects like Nexus Raven, Toolformer, and Gorilla have shown that smaller models can effectively call external APIs. Fine-tuning language models has become common practice, with methods like LoRa offering extended functionalities and potential for adaptation to various applications. Section Summary. In this section, we explore the rapid advancements in AI agents, particularly in function calling, with the emergence of large language models like Multion and Adept AI. While these models showcase impressive capabilities, concerns around privacy, inference costs, and reliance on cloud models persist. To address these challenges, a trend towards deploying smaller models on edge devices is gaining traction, with our method demonstrating enhanced accuracy and reduced latency for function calling on 2B parameter models, offering significant improvements in battery efficiency and performance compared to GPT-4. Section: Methodology. In this section, we detail the primary methodology we used in our models and explain how we collected the dataset to fine-tune these models. We provide examples from the Android API to illustrate our process. We then discuss how we trained our model, treating the causal language model as a classification model. To successfully use a function, we need to choose the right function from all available options and generate the correct function parameters. This involves two stages: selecting a function and generating parameters. Initially, we understand the function's description and its arguments, using information from the user's query to create parameters for a function. One approach is to combine a classification model with a causal language model. We can view the available functions as a selection pool and turn the selection task into a classification problem. For classification, we can use methods like document selection based on similarity or mapping the query to a function name. Another option is to use autoregressive models like GPT to predict the function name from the user's query. These approaches split the task into two parts, possibly needing two models, pi_1 and pi_2. To simplify, we set pi_1 equals pi_2 equals pi. Our goal is to predict the function name given the query and model pi. Traditionally, finding the right function involves retrieving relevant functions and providing context to determine the best function names. When using a language model to generate a function name, multiple tokens may be needed, leading to errors. To address this, we assign unique tokens to functions, simplifying the prediction task to a single token classification among functional tokens. We incorporate these tokens into the model and modify it to predict the correct function token. By training the model with function descriptions, it learns the importance of these tokens. This method also allows for parallel and nested function calls. An important advantage of this methodology is that once the model understands the functional tokens, it can stop early using a special token, less than nexa_end greater than, avoiding the need to analyze function descriptions. This significantly reduces the tokens required to identify a function name. The difference between our model and the conventional method is illustrated in a figure. Moving on to dataset collection, we explain how we gathered high-quality datasets for training, validation, and testing. We focus on Android APIs, selecting 20 APIs across system, app, and smart device management categories. We organize these APIs based on usability and technical complexity, ensuring they can be executed on Android devices. Our dataset creation involves generating relevant queries and function call arguments, as well as incorporating positive and negative examples for model training. We maintain a balance between positive and negative samples in our dataset. Despite the capabilities of large language models like GPT-4 and Google's Gemini, errors can occur, especially in generating function call arguments. To address this, we implement a verification system to evaluate and regenerate function calls if needed. Section Summary. In this section, we outline our primary methodology for model implementation, dataset collection, and model training, focusing on the Android API. We emphasize a two-stage process involving function selection and parameter generation, proposing a unified GPT model strategy for quicker inference speeds. By introducing unique functional tokens and modifying the model architecture, we enhance function name prediction accuracy while reducing the number of tokens required. Our dataset collection process involves assembling high-quality datasets from Android APIs, categorizing functions, and generating relevant queries and function call arguments for training and validation. Section: Model Development and Training. In this section, we utilized the Google Gemma 2B model as our pre-trained model. Our training process involved two methods, full model training and LoRa model training. We used the Atom W optimizer with a learning rate of 5E5 and a warm-up step of 10 for both training methods. The LoRa rank was set to 16, and we applied LoRa to specific modules with the LoRa alpha parameter set to 32. We conducted training for 3 epochs for both methods. Our experiments focused on evaluating language model capabilities for generating accurate function calls. We compared our model's performance with leading models like GPT-4 and GPT-3.5. We also explored the effectiveness of the RAG technique in reducing incorrect outputs and latency by providing language models with a concise selection of potential functions. By integrating Meta's FAISS for semantic search, we improved function call description retrieval, considering constraints on context length. We also studied the impact of training dataset size and methods on performance metrics. For our study on Android function calls, we concentrated on accuracy and latency in function call generation using 20 Android APIs. We employed a RAG approach to identify similar function descriptions based on user queries and evaluated various models. Our benchmark results highlighted accuracy and latency metrics, showing improvements in performance. In evaluating the Llama 7B model, we found limitations in generating expected outcomes, leading us to fine-tune a variant for function call generation. Despite efforts to guide the model towards accurate function generation, the accuracy rate was modest. We implemented optimizations to improve latency, such as flash attention and a fast tokenizer. Similarly, with the GPT 3.5 model, we achieved high accuracy and significantly improved latency for generating function calls. By including all function descriptions directly in the context, we reduced latency further. The GPT-4 model exhibited superior accuracy and lower latency than GPT 3.5, indicating potential resource allocation differences. Introducing the Octopus model with 1,000 data points sampled for each API, we observed high accuracy in our evaluation dataset. The Octopus model demonstrated reduced latency due to its compact size and efficient mapping of functional tokens to function descriptions. By deploying the Octopus 2B model on mobile devices through quantization, we achieved remarkable performance in completing function calls swiftly. Section Summary. In this section, we utilize the Google Gemma 2B model for our framework and implement two training methods: full model training and LoRa model training. We specify training details such as optimizer settings, learning rates, and epochs for both training approaches. Additionally, we conduct experiments to evaluate language model capabilities in generating accurate function calls, comparing our model against GPT-4, GPT 3.5, and exploring the impact of the RAG technique on reducing incorrect outputs and latency. Section: Extension to Vehicle, Yelp, and DoorDash function sets. In this section, we extended our evaluation to include Vehicle, Yelp, and DoorDash function sets. We added 20 vehicle function calls to showcase how adaptable our algorithm is to different use cases. For vehicle functions, we focused on important control methods like adjusting volume, air conditioning, and seat positioning. Our benchmarks for vehicle functions mirrored the Android function evaluation, showing consistent performance patterns. Details on vehicle functions can be found in the appendix, allowing users to customize new sets of functional APIs to suit their specific needs. Additionally, tests with Yelp and DoorDash APIs confirmed similar performance, highlighting the versatility of our method across various function sets. The Octopus model performed exceptionally well with 1,000 data points sampled for each API during training. However, when training new functions, cost efficiency becomes important due to the need to generate a training dataset. Our analysis showed that generating 1,000 data points for a single API costs $0.0224 United States dollars, which is the investment needed to train an OCTOPUS0 model for one specific function. By evaluating different models, we found that sampling only 100 data points for one API can still achieve 98.095% accuracy. Therefore, we recommend a dataset size ranging from 100 to 1,000 data points for individuals looking to train their own Octopus model using our framework. LoRa plays a vital role in our framework, especially when integrating the Octopus model across multiple applications to ensure smooth computation. Instead of using full models for each API set, we opt for diverse LoRa trainings tailored to the specific function setups of different apps. While switching to LoRa training may result in a slight decrease in accuracy, the high accuracy levels maintained are robust enough for production deployment. For parallel and nested function calls, we need to prepare 4,000 data points for each API to achieve the same level of accuracy as a single function call. Our approach involves incorporating special tokens into the tokenizer and expanding the language model's head. We use a weighted cross-entropy loss function to address the challenge of an imbalanced dataset during model training, where special tokens receive elevated weights compared to non-special tokens. Early-stage training experiments show that increasing token weight can speed up convergence. Our research demonstrates that any specific function can be encapsulated into a functional token, seamlessly integrated into both the tokenizer and the model. This cost-effective training process enables the deployment of AI agents with low latency and high accuracy. The potential impacts of our research are significant. offering application developers the opportunity to train on application-specific scenarios and automate app workflows efficiently. Looking ahead, we aim to develop a model dedicated to on-device reasoning, focusing on speed enhancements for cloud deployments and supporting local deployment for privacy and cost savings.